Hey out there, welcome to Deja Vu, it's Algebra 2. As always, I'm your host, Kevin Corpy, here to take you on a fantastic mathematical journey. Now today is lesson 13, so I hope you don't have triskaidekaphobia, huh? That's the fear of the number 13. Because if you do, I'm just going to tell you, it's all in your imagination. And why is imagination important on today's show? Well, because we're going to be talking about imaginary numbers. Yeah, these are actually things that we're going to be looking at and feeling and talking about, but they are still called imaginary. You're going to see why we call them imaginary and how they are important. So if imaginary numbers are kind of intriguing to you, download the worksheets from the district website, stick around for about 30 minutes and do some math with me. Okay, lesson 13, complex numbers and imaginary roots. Well, the whole thing that's going to drive today's lesson is a very important theorem that I talked about on last year's geometry show called the fundamental theorem of algebra. It's an important theorem that was first proven by Carl Friedrich Gauss at the age of 19. He earned his PhD using that. The implications of it, though, are profound. So here's what it actually says. And we're going to tailor it specifically. We're going to rephrase it a little bit from the original phrasing, and we're going to tailor it towards quadratics. So here's what it says in terms of quadratics. If a quadratic equation does not have any real x-intercepts, that means if it doesn't cross the x-axis, which is a real number line, then the roots, or the x-intercepts, have to all be imaginary. And in this case of degree 2, there's going to be 2. So what the theorem really says is, later on, any polynomial of degree n is going to have exactly n complex roots. Now, complex numbers are either going to be real numbers or imaginary numbers or combinations of the two. We're going to talk about those today. So for instance, if we look at this right here, the equation x squared plus 1. That is a parabola, x squared, and what's the transformation? The plus 1 moves it up 1 unit. So the vertex is at 0, 1. Now remember, if we're looking for x-intercepts as solutions to the equation, when I set it equal to 0, those are the roots, those are the zeros, then where does it cross the x-axis? Well, it doesn't, okay? But the fundamental theorem of algebra tells us that it has to have 2 roots or 2 solutions. And so if they're not real numbers, they're imaginary numbers, or they're complex numbers. And so the question is, how are we going to find those? Well, let me show you. If I come back over here and I set my equation equal to 0, I can solve. And since there's no x term, I'm going to use algebra. So I get x squared equals negative 1, and I'll take the square root of both sides. And when we extract the square root for x, we have to remember to take both the positive and the negative version. So I get the square root of negative 1. Now you've learned up to now that, hey, you can't take the square root of a negative number. It's undefined. It doesn't exist. Because what that means is you have to have a number that you can multiply by itself and get a negative number. And the product of 2 positives is positive, and the product of 2 negatives is also positive. So how can we do that? Well, here is where the need arose to invent something, okay? Invent a notation for this. And that's where we get the square root of negative 1 defined to be the imaginary unit that we call I. Now notice on the real number line, we can't put these i's, plus or minus I, positive I, negative I, anywhere on this coordinate plane, because this is a real number line. There is, however, a complex number plane, which we're not going to get into today, and it's a way to actually see these solutions. But don't expect on a real number line, Cartesian plane, to actually see the imaginary x-intercepts. But you know they're there. And notice that these are 2 of them. You get a conjugate pair of complex or imaginary solutions. Positive I and its conjugate, negative I. Okay? Plus or minus I. So what can we say here? We are specifically defining, by definition, for the square root of negative 1 to be the imaginary unit. So the square root of negative 1 is I. All right, so imaginary numbers. I. What the heck are these? Okay, where did they come from? Who invented them? Well, it was actually René Descartes who actually gave us the terminology imaginary numbers. Now, when he called it imaginary numbers, he meant it almost as a slam, as a derogatory comment towards these roots that we couldn't see. He's like, oh yeah, the roots exist? Yeah, what are they? Imaginary? And eventually the name stuck and it kind of lost its negative connotation. So imaginary today, we don't fear imaginary numbers anymore. Now, where did we get the symbol I? Well, that was Leonhard Euler, the most prolific mathematician of all time. he gave us the letter I. He started using it as a variable. Now, where did he get the letter I from? Well, at the time, I think the Latin term for imaginary was imaginarius. So imagine where he got the I from. No bonus points for getting that. Okay. So anyway, it was a tag team effort between René Descartes, who gave us the name, and Leonard Euler, who gave us the I, the unit itself. Now, you might be saying at home, so what? What are these imaginary things? How are we going to use them in the real world? Well, look at this, for example. When rational numbers first came on the scene, those are the fractions. People really didn't have a context for what they are, like 1/2 or 2/3. Those numbers really don't make sense in the context of like counting people in a room, counting whole objects. But when you talk about slicing up a piece of pumpkin pie, then I ate 3/4 of the whole thing, makes a lot of sense. Ooh, tummy ache, okay? So fractions in a certain context do make sense. And once you're familiar with the context, those numbers become less fearful, okay? What about negative numbers? Negative numbers don't make sense in certain contexts, like if you're talking about people's weight or people's age. But when you're talking about money, then all of a sudden, negative numbers take on a whole new meaning. It can represent debt, or it can represent a net change in the value of a stock. So now in that context, more experience with negative numbers, they become less fearful, they become more commonplace. Well, believe it or not, imaginary numbers might be foreign to you, but most people don't encounter imaginary numbers in the context of normal living. So where do they show up? Well, there's many applied fields of science that do actually involve imaginary numbers. Fields such as electromagnetics or quantum mechanics, even cartography, the art of map making, involves imaginary numbers. Electrical engineers, if you talk to one, they could tell you that they actually use negative numbers on a regular basis. They actually represent electrical current, and imaginary forces called phasors are actually imaginary numbers. Okay? And although they are imaginary in the context of the calculations, the phasors themselves are very real currents that can actually injure people or damage equipment. So the mathematics behind it, though, does deal with imaginary numbers. So unless you're in the context of working with them on a regular basis, they're probably always going to be a little bit mystical to you and unfamiliar. So the best you can hope for is just to deal with it, get used to them, and learn how to use them correctly. All right, so here's an example. We have a function g of x. It's a quadratic, x squared. We're multiplying it by 9. Remember, that's going to be vertically dilated. And then plus 25 moves it up 25. So we want to find the zeros. Well, the fundamental theorem of algebra says that if it's degree 2, quadratic, we're going to have 2 of them. Okay? If they're not real, they're going to be imaginary or complex. So to see what this graph looks like, we can go up to 25, and then we can draw it vertically stretched by a factor of 9, which is going to make it very, very steep. So again, notice there are no real x-intercepts. Therefore, by the fundamental theorem of algebra, there's going to be 2 imaginary solutions. And how do we find them? Well, again, we set the equation equal to 0. There's no x term, so just like before, we will subtract the constant, and we'll divide through by the coefficient of x squared. So we get negative 25/9. When we take the square root of both sides, extracting both the positive and negative square root, we get the square root of negative 25 over 9. Well, where do we go from there? That's a negative number. So what we can do is we can think of this as a negative 1 times 25/9, so the radical. So this becomes plus or minus the square root of 25 is 5, the square root of 9 is 3, and the square root of negative 1 is I. So we get another conjugate pair here of solutions. They're both imaginary, positive 5/3 and negative 5/3 I, that is, 5/3 I. And again, don't expect to see them on the real number line. There's 2 of them, so we know we found both of them. The search is over. Fundamental theorem of algebra tells us degree 2, quadratic, 2 solutions. If they're not real, they're imaginary. Okay, now what I did right here is I was working with radicals, and that's something that you need to kind of develop a little more confidence with, perhaps. So let's just kind of practice this right here. Simplifying radicals. What you want to do is, if it's not a perfect square under the radical, you want to try and find factors of it that are perfect squares. Now notice there's not a negative under this radical. So 75 is, let's see, 25 times 3. 3/4 is 75 cents. So you can write that as negative 25 times 3. Well, you can write that as negative 25 times, or square root of 25 times the square root of 3. And 25 being a perfect square, we get negative 5 square root of 3. There we go. And that's simplified because 3 has no factors that are perfect squares. Let's look at this one here. This is negative square root of 42 over the square root of negative 3. Ooh. Okay, so one thing we can do is we can put each of them under the same radical. And what we want to do is try and find factors of 42. Well, 42 is 7 times 6. That one should jump into your head. 7's prime, but 6 is the same as 3 times 2. So if I can get the prime factorization up there, life's going to be easier. And on the bottom I have a negative 1 essentially times 3. Well, we can divide out common factors, so those 3's are gone. So what we're left with now is negative square root of negative 14. Well, 14 is not going to have any perfect square factors. It's just 7 and 2. But we can take the negative out from under the radical. And that becomes negative square root of 14 times I. I is outside the radical. And that would be simplifying it. So now we don't have a negative under the radical because we've got the I on the outside. Got it? Here's one more. 5 times the square root of negative 32. Well, the negative under the radical means that we're going to have an I on the outside. But square root of 32, does it have any perfect square factors? Well, with a little investigation, you'll see that 32 is 16 times 2, where 16 is a perfect square. So we can write this as 5 times I times the square root of 16 is 4, and that leaves the square root of 2 under the radical. And now we can combine this, and I get 5 times 4. That's 20I times the square root of 2. And that's okay, but if you want to write your I at the end, that's 20 square root of 2 times I. Just make sure that you have your I outside the radical, distinctly outside the radical. And there you go, working with radicals. A little practice and it'll come naturally to you eventually. So, what are these complex numbers? Complex numbers are basically the largest set of numbers that we use in all of mathematics. They're composed of all the real numbers, they're composed of all the imaginary numbers, and combinations of them. So if you look at this little diagram here, we start off with the natural numbers, n, that's 1, 2, 3, 4, 5. And there's also a set of whole numbers, which are basically the natural numbers including 0. Then we step up from there and we got z, the set of integers, and that includes all the positive and negative natural numbers, including 0, negative 1, negative 2. Then we got the set q. Q is for quotient. Those are going to be your rational numbers. Those are going to be the quotients of your integers, like negative 5/3, 2.5, all your terminating repeating decimals. And then we have r. Those are going to be your real numbers. Okay? Now the real numbers are the largest set of non-imaginaries that we use. And then inside the reals, but outside of q, we have the irrationals. Those are like the square root of 2 and the square root of 3. Over here we have this disjoint or mutually exclusive set called the imaginaries. Those are all the ones that have square roots of negatives. And there's no overlapping here. If we combine those two together, we get this, which is the set of complex numbers that we write like that. They could be all real or all imaginary, or any combination of them will lie out here. So here's the definition. A complex number is anything that can be written in the form a plus bi, where I is the imaginary unit, the square root of negative 1. And a and b are real numbers. A is going to be called the real part, and b is going to be called the imaginary part. So if a is 0, we have a strictly imaginary number. If b is 0, we have a strictly real number. But we can also have a and b being non-zero, and then we have a complex number. So for example, the number negative 4. That's an integer, it's a real number, it's also a rational number, but since I can say plus 0i at the back, I can write it as a plus bi, so it's complex. Negative 5i, that's a strictly imaginary number, but since I can write it as 0 plus negative 5i, it's also complex. And 2 minus 3i, well that is a complex number. 2 is the real part, 3 is the imaginary part. And this one here I have written a little bit backwards, but just by rewriting it, negative 7 minus the square root of 5i, I've written it in a plus bi format. So that's also a complex number. All right, let's take a real quick break, but we'll be right back. Don't go away. While you're gone, think about this. Leonard Euler, the guy I just talked about in the show, the most prolific mathematician of all time. He worked so diligently at so many math problems that he eventually went blind in one eye. And when he went blind in one eye, people asked him, hey, Mr. Euler, what are you going to do now that you have lost the sight in one eye? And he said, the answer when you get back.
The odds of a child becoming a professional golfer? 1 in 140,000. The odds of a child being diagnosed with autism? 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy. Did you think about what Leonard Euler might have said? How funny can a mathematician be, huh? Well, when Leonard Euler lost sight in one eye and he was asked, what are you going to do now that you've lost sight in one eye? He said, well, now I shall be less distracted. Yeah. Incidentally, he went on to do many, many, many more volumes of math, really good quality math work after he lost sight in one eye. So, good sense of humor and a great mathematician. Anyway, back to imaginary numbers. All right, so before we start looking at equations, you need to develop a little bit of agility and familiarity with working with imaginaries. So here we go. We're going to look at powers of I to begin with. And we're going to start with I to the first. I to the first is the square root of -1 by definition. If I square both sides, I get I squared is -1. So normally in the real world, can't square a number and get a negative. Imaginaries, it's possible now. Well, I cubed, well, how are we going to get I cubed? We're going to multiply both sides by I, and we get negative I. And that's equal to negative square root of -1. But what we're going to try and do is write everything in terms of I. So I cubed is equivalent to negative I. Now this one's really nice. I to the fourth. If you take I squared equals -1, and you square both sides. I squared squared is I to the fourth. -1 times -1 is +1. So I to the fourth is +1. And it's always nice to walk around a math class with a bag of clever forms of 1 at your disposal, because they can always come in handy. Here's a clever form of 1. Well, after that, things start repeating themselves. I to the fifth is the same as I to the fourth times I, or just I, because I to the fourth is 1. So we basically start this repeating pattern after a while. So that will allow you to do something like this. I to the 263rd, well, all you have to do is take 263 and divide it by 4. Why 4? Because it repeats itself every 4 exponents. So now we go 4 into 26, that's 6. That gives us 24. 4 into 23 goes 5. 20. We get a remainder of 3. That remainder right there is going to be your new exponent. So I to the 263rd is equivalent to I to the third. Well, I to the third is equal to negative I. So what you want to be able to do when you're working with imaginaries is to never leave in your final answer any power of I greater than 1. Because you can always reduce it down to either an I, a negative I, a 1, or a negative 1. Okay, so now that we know how to work with imaginaries, we're going to work with complex numbers. We can actually do operations, addition, subtraction, multiplication, and division. So let's say we have these two complex numbers. U is 2 plus 3i, V is -1 plus 5i, and U with a bar written over it is the notation for the conjugate of U. Okay? And the conjugate of U is basically 2 plus 3i. Sorry, 2 plus 3i. I'm sorry. Let me back up here. If U is 2 plus 3i, then its conjugate is going to be 2 minus 3i. We're just changing the sign of the imaginary term. Okay? So that word, again, is the conjugate of U. That's what U bar means. Okay? And I'm going to show you what happens when we multiply two conjugates together. But first, let's add them. U plus V, well, that's going to be 2 plus 3i plus -1 plus 5i. And if you want to put them in grouping symbols, that's fine. But we're going to treat these like we do algebraic expressions, like we do with x's and y's. We can essentially add the like terms. So the numbers, 2 minus 1 is 1. 3i plus 5i is 8i. And there's your answer. So we get a brand new complex number. Subtracting them we can do, and we can also multiply by a scalar multiple like 3. So negative 3v is going to be negative 3. V was -1 plus 5i. Minus u, not me, but u, we get that. So what we're going to do is we're going to distribute. We get a 3 plus 15i minus 2 minus 3i. Distribute the negative. And now again we can add like terms. 3 minus 2 is 1. And 15, ooh, I missed something here. Negative 3 times positive 5. Whoops, that's a negative. Okay? Going too quickly, you can make careless mistakes. All right, so that's a negative 15 minus 3. That's going to be a negative 18i. All right, haste makes waste. So they say. Let's try multiplying. This is where it gets interesting. U times V, that's 2 plus 3i times -1 plus 5i. Now, we can essentially use the FOIL method, although I don't like to call it that. It's essentially what it is. It's a product of two binomials. So if we multiply the first, we get -2. The inner is going to give us -3i, and then we get plus 10i, and then the outers are going to be plus 15i squared. Well, we can collect these like terms, 3i and 10i. That's going to give us -2 plus 7i. Now notice what we have here. we've got 15i squared. Remember, we don't want to leave anything with a larger power than 1 on our i's. So what is I squared? Well, remember that I squared is negative 1. So 15i squared is the same as 15 times negative 1, which is negative 15. Aha! So now negative 2 minus 15 we can combine to get negative 17 plus 7i. And that has the number written in a plus bi, or standard complex format. Okay, so I squared you don't want to leave. What about u times the complement of u? That's what u times u bar is. Well, that's going to be 2 plus 3i. That's u. Its conjugate is 2 minus 3i. You change the sign of the imaginary term. Well, we're going to use FOIL again here. 2 times 2 is 4. The product of two conjugates, look what happens to the middle term. You get plus 6i on the inners, and you get minus 6i on the outers, and then we're going to get minus 9i squared on the last. Well, these are opposites. They make a zero pair, so see ya, wouldn't want to be ya, 6i. And we're left with negative 9i squared. But if I squared is negative 1, then negative 1 times negative 9 is positive 9. So this becomes 4 plus 9, or the number 13. Okay? So what's nice, when you multiply the product of two complex conjugates, you get a number, a single number. Pretty cool. Now that's going to come in handy down here when we divide. Let's do v divided by u. That's negative 1 plus 5i divided by u, not me, which is 2 plus 3i. Now we want to get in standard form, so we want to get rid of this 2 plus 3i out of the denominator. So what we're going to do, here's where those clever forms of 1 that you're carrying around come in handy. What you want to do is multiply by the conjugate of the denominator. So we have 2 plus 3i there. We're going to multiply by 2 minus 3i and 2 minus 3i. And watch what's going to happen. In the numerator, I'm going to expand. So I get negative 2. I'm going to get a 10i plus a 3i. That's going to be plus 13i. And then at the end, I get negative 15i squared, which is really positive 15. All over the product of two conjugates, that's going to be a 4. Your 6i and minus 6i's go away, and we're left with negative 9i squared. Now in the numerator, notice what happens. 15 minus 2, that's 13 plus 13i. And at the bottom, I squared is negative 1. So that's really 4 plus 9, which is 13. And we're almost there. I can split up the numerators now. 13 divided by 13 is 1, plus 13 divided by 13 is 1i. So that simplifies to 1 plus I, and that's standard form.
Deja Review.
Here's what we want to do. We want to solve the following quadratic equation using each of the methods that we've learned on this show and in previous shows, which includes factoring, completing the square, using the quadratic formula, and graphically. All right? These are a bunch of different methods. They're all going to accomplish the same thing. So here we go. If you're going to do it by factoring, this is a quadratic. You set it equal to 0. You're trying to factor it into its prime factorizations. And the first rule of factoring is to look for a common factor, either variables or numbers. There is a common factor of 2 all the way through, so that becomes x squared plus 7x plus 12. Now you're focusing in on this little trinomial with a leading coefficient of 1. That makes it a little bit easier. So 12 is your target product. Factors of 12 that add to 7, 4, and 3. So that becomes 2, x plus 4, and x plus 3, and they're still equal to 0. Now the zero product property says anything multiplied equaling 0, you can set them each equal to 0. So does 2 equal 0? Haha, remember it doesn't. It's a number. But x plus 4 could equal 0, or x plus 3 could also equal 0, which means x can equal negative 4, or x can equal negative 3. And those are going to be the two solutions. Those are the two real x-intercepts. Fundamental theorem of algebra says we found 2. The search is over because it was degree 2. We can expect 2 roots. And in this case, they're both real. You can actually sketch what the graph looks like now because you know your x-intercepts. 1, 2, 3, and then 4. And it's a leading coefficient that's positive, so it opens up. There you go. And by symmetry, you know the vertex is going to be halfway in between there. So we really don't know at this point how far down it dips, but there's what the graph looks like just from the x-intercepts. All right, completing the square, that's always fun. To complete the square, we have to have the leading coefficient equal to 1. So I have to factor out the 2 from the 2x squared and from the non-squared term, 7x. But then I'm going to complete the square inside, and then I'm going to turn around and subtract something, or add the opposite, plus 24 equals 0. Now by doing that, remember how we do this. We take half of the 7, which is 7 halves, and we square it, which is 49 fourths. Now, I don't want to put negative 49 fourths here because I have to multiply it by 2. So this is going to be 49 halves. All right? Times 2. So this now, we've created a perfect square trinomial. That's x, square root of x squared is x, square root of 49/4 is 7/2, and the sign of the middle is positive, so it should work like that by design. Now over here, we need a common denominator. 24 in terms of halves, well, that's 48 halves. Oops, and I need to subtract it. Oh, that's positive, this should be negative. So 48 halves minus 49 halves is going to be negative 1/2. All right? Now it's still equal to 0. So what I can do now is I can start doing a little bit of algebra. I can bring the 1/2 to the other side. I can divide through by 2, and I get 1/4. And now I'll take the square root of both sides. So I get x plus 7/2 equals the square root of 1/4 is 1/2. And I got to remember to take the positive version, or x plus 7/2 equals the negative version. All right? Well, now I have two equations. They're both linear. I can solve them. So I get x equals 1/2 minus 7/2, which is negative 6/2, or negative 3. And x equals negative 7 minus 1, which is negative 8/2, or negative 4. Do you like that method better? Well, if you really like the algebra involved because it's fun, you might. But in this case, I think factoring was probably the way to go. But this is still a viable method. All right, quadratic formula. That's one that you probably already have memorized up in your head. And this works every single time you have a quadratic, so long as you have it written in descending order in standard form. Here it is. I'm going to go off to the side and identify my a, b, and c. A is the leading coefficient, b is the coefficient of the non-squared term, and c is the constant. So we identify them all. Now, you could actually, if you wanted to, factor out a 2 first, and it'll make your a, b, and c a little bit smaller. But if you don't see that, that's fine. It should work this way as well. So x equals the opposite of 14, plus or minus the square root of 14 squared minus 4 times 2 times 24, all over 2 times a, which is 2. Now, we're running out of time here, but you could do these calculations, and I hope that you would get the correct answer. Let me show you what those are going to be. Calculator might help you with some of these large numbers. You're going to get negative 14 plus or minus 2/4, which is basically negative 14 plus 2 is negative 12/4, or negative 14 minus 2 is negative 16/4. And so again, that equals negative 3 or negative 4. We get the same two solutions. So quadratic formula always works, but sometimes the numbers can get kind of daunting, and it's easier to try and do it by factoring if it works. All right? Let's look at graphing down here. Graphing, we know how to use the graphing calculator. So all we'd have to do is put our left side of the equation into the calculator for y1. Hit zoom 6, standard viewing window, and you can narrow your window down to get it to look like this. Now your calculator can actually find zeros for you. If you hit second, trace, which is at the top of your calculator, the second button, trace, and if you hit number 2, you'll actually see the 0 command sitting there. And we've done this on previous shows. It'll ask you for a left bound and a right bound. So if you're trying to find this one, left bound, enter, right bound, enter, hit enter for your guess, and it'll actually give you this window right here. It'll tell you the 0 is at negative 4, and there's the y equals 0. So we know that that's one of the roots. You repeat the process for this one, except this time your left bound is below and your right bound is above, because you always read a graph from left to right. And then you hit enter for your guess, and it'll tell you the other 0 is at negative 3. So there you go, solving it graphically. Okay, so that last example there, we did it in multiple ways. What you need to know is definitely how to actually do each method. But more importantly, perhaps, is when to use each method. Because different scenarios are going to actually be a little bit easier, more efficient, if you use one particular method over another. Okay? So how are you going to know that? Well, you get really, really good at the skills by doing a lot of problems. And after you do that, again, you pick up on the nuances, and you'll start developing some strategies as to when to use one method or another. Okay? Well, we are unfortunately out of time today. Hope you learned a lot, and I hope you'll join me next time for another episode of Deja Vu, It's Algebra 2. So until then, I'm Kevin Corpy reminding you to do your homework.